currently 1 p.m. Me and Dexter are going to be your hosts for today. We'll be going over assemblies, and we'll actually be making a gearbox towards the end. So, Dexter, would you like to start the presentation?
Sure thing. So, welcome back, everybody. Same deal as last time. So the first few slides, just make sure that you're all signed into your on-chip accounts and ready. And then once you're done so, just say that you're ready in the chat.
All right, so it looks like mostly everyone's ready. We'll give a bit of extra time just to make sure everyone's here. This is true. It does indeed help a lot to have 2 screens. All right, so I think that's about everyone. So let's get on to today's lesson. We'll start off by reviewing stuff that Dexter went over last class, and then we'll get into like how gearboxes work, so we like understand what we're going to make. And then for the last part of the lesson, we'll actually be designing a gearbox from scratch.
Okay, so in our last lesson, we covered assemblies as well as what mates are. And so for review, mates are used to constrain 3D geometry to each other in different ways, meaning that you pull in 2 parts into an assembly and then make them connect or interact in different ways. For example, the fasten mate to make them have no movement between each other, or the revolute mate to make one piece revolve and only revolve around another piece. And we also learned that these parts, you can import them from your own files, from your own documents, as well as from the public domain. And so one of the more helpful public domain options we have is by looking up MKCAD in the public domain search bar, and it's going to be a part library with a bunch of very useful parts that has a target focus towards FRC teams. But the stuff in there can be universally useful. It's got stuff like a bunch of different kinds of pulleys, a bunch of different kinds of gears, motors, wheels, bearings, brackets, all that kind of good stuff. So yeah, so you just look up MKCAD. It takes a while to load. That's just how these things are. And then you'll see that this menu pops up. You have all these different options. And if you click on one of them, it'll bring up more detailed options within it. So it's not much an encoder, but yeah, it just takes a bit to load to get back, but it opens something like bearings or pulleys, hubs, sprockets. It's going to bring up a bunch of different other kinds of options of different types of different dimensions that can be useful for your assemblies. Mhm.
So now that we've gone over, I think, about everything that we learned in the last lesson, we'll be learning a new thing that I forgot to teach you guys. The whole wizard, we all love making holes and stuff, right? So you can like bolt stuff together, or say I want like this thing to attach to this other thing in X or Y place. I can have a hole. I could just put a bolt through the hole when I'm actually building thing, and it just works, you know. Um, so so let's start by, well, I guess first just make like a quick little plate. I'm going to use my standard for these demonstrations of a 5x5 plate. Um, why is, oh, looks like I did a dumb, well, all right, so um, let's extrude this out. Let's, actually, there's a better way to demonstrate this. Let's not make a plate. Let's make some like aluminum extrusion. We're gonna have two rectangles inside each other. So that's not what I meant to do. Let's have the outer one be 1 inch, and then distance between these, let's go with 1/16. And then to make sure that it's actually square, let's do that. So let's extrude this. Let's just extrude it out 4 inches. Sounds about good to me. So now I have this piece of aluminum stock, and let's say I want to make a hole in it, and I have a particular place I want the hole to be, but due to how I created the like sketch, I can't like put a hole in it myself, or I just don't know exactly how large I want the hole to be. I just know I want it to fit like a certain size bolt or something. Um, so this is more useful for the bolt, where like, oh, I want to have a hole for a 1032 bolt, and I need it to be in this place. I don't want to memorize the exact diameter of a circle I need to make for a proper sized hole for a 1032 bolt. There are far easier ways to do this. The, this is the way. Um, so first, I will create a sketch on the face I want to do this on. I'll just go with the right face for now, and then I'll put a point. Let's go with on the center line here to have one there and one there. Um, then I want these to be a certain distance from this end. So I'll start by dimensioning this point. Let's put it at 1 inch. That sounds good to me. And then let's put this one at 1.5 inches. So it's slightly offset from like the center. Okay, so now that I have my points defined, and keep in mind this could be pretty much any point you want, as far as I know. I need to first save the sketch so it actually um, is a feature in the model. Then I go up here. There's a box with a circle going through it that says hole. We are going to click on this, and then there's this whole dialogue that comes up like, oh, want like a simple counterboard, countersink, through blind, blind and last, which is complicated. We're not going to go over that today. Various standards you can choose. most of the bolts that our team uses, at least, are the ANSI standard ones, which is the like imperial inches type standard bore. However, ISO is if you have like an M2, M3, any like metric size bolt, but we'll be using ANSI today because that's what I'm a little more familiar with. And we want to make let's go with a clearance hole for a number 10. And this is going to be a free fit, so we can just easily put in the bolt. And let's say I want it to be there. Onshape's going to load a bit, and then now you see I have this hole here. It goes all the way through because it's a through hole. And this hole is perfectly sized to accept a number 10 size bolt. So if I want a like 2-inch 1032 bolt, it'll fit right in there. So also work for like 1024 or like whatever other tooth you happen to have. And then since I can also say, oh, maybe I want another one of these right next to it, I'll click on this hole here, and that adds this point here, and that will add that point to the list of points that I want to put holes in. And so now I have both the holes right next to each other, and as you can see, yeah, this makes it a lot easier to create a hole for like a certain size bolt, or if you need it to be somewhere but you don't want to just like do it yourself. It just makes a lot of things easier.
Okay, so for today's lesson, the practice activity is going to be a bit different from how they were in the past. Instead of giving you something external to do after everything's done, we would like to try and follow along as the gearbox is created during the lesson. And if by any lesson out of time and you haven't quite caught up, you can always go to the resources document to find the video upload for the lesson. And don't worry, we'll make sure to go slow. And if you have any questions along the way, we'll make sure to answer them to the best of our ability.
All right, so we're going to start with like components of a gearbox. So like, how do they work? Well, gears, gears in the name gearbox, it's probably fairly obvious that they're there. They like drive the gearbox, and they take in mechanical power, and they can like upscale or downscale. For example, if you had a large gear driving a small gear, one rotation of the larger gear will be like more rotations of the smaller gear, so it'll turn faster. However, since we can't just get infinite, like oh, I'll just have this turn super fast, and I could use this for like whatever high speed turning thing I want. Um, that doesn't entirely work, because as you increase the speed, the force behind the speed gets decreased. It's called torque. So like as you gear something to spin faster, it's not as strong, and there's less torque to like turn something else that thing would need to turn. And conversely, as you gear stuff to turn slower, the torque increases, so it gets stronger. Then the plate, that's like, well, I mean, that's also fairly self-evident from the name, I'm guessing. That's like the part that holds the gearbox together. They're actually, I'll just get a proper gearbox over here so I can explain what I'm talking about a little better. So like this here is the plate. This like holds everything where it needs to be. It can help prevent other things from like reaching in, messing with it. It can help prevent stuff from coming out. So for example, like if part of this breaks, or so say there was like something on this axle that I didn't want to like go out and like leave the gearbox, I could like fill in like this hole here, so there's no way for it to actually get off the axle and just go wherever else it wants to be. Then the next important part of a gearbox is a motor. These are also probably fairly obvious, because I mean, how are we going to get power into the gearbox? Of course, motors. The one we'll be designing today has two. Common gearboxes for FRC can range anywhere from 1 to 3 gearboxes I've seen. Um, at least 3 is the most I've seen. I'm sure someone's tried to put 4 in at some point. So then finally, the encoder. And encoder is an electrical device that measures rotation. So say you want the robot to go forward like a certain distance. Assuming you know the gearing of the gearbox and like the diameter of your wheels, you can figure out how far the robot has traveled by figuring out how far, say, this like central shaft here has rotated. So if I'm trying to put an encoder on here, I'd probably put it like around there, over here, maybe. There's just a couple of different places you can put it. Thankfully, the motors we will be using today, which is a Neo 550, I think a Neo 550. Well, the Neos, they have encoders built in, which is super helpful, although they're not quite as accurate as like a purpose-built encoder. So if you want the like high precision, you might want to look into actually building a mount for a proper encoder, figuring out how those work.
Okay, so before we move on, we want to quickly also cover some kinds of gears you might see. These are just 3 gears that are fairly common. The first one is the spur gears. These are the gears you've probably seen the most often and the ones we'll be working with today. And they're just cylindrical gears, which is straight and parallel to the shaft. So as you can see, the teeth kind of straight on. These guys will just rotate fairly simply. Then you have the helical gears, which are similar to the spur gears, however, the teeth are winding. As a result, they're more quiet and they mesh better and can do higher loads. However, however, they'll end up producing some axial force, and so what that means basically is that as they're spinning, they'll also produce force that's running along the shaft they're connected to, and so you need specialized bearings to negate that. So that's a bit of the drawback. And then a bit more of a different one is the gear rack, which is comprised of the rack itself and then a pinion. And so what this does, it allows you to convert rotational motion into linear motion, because as the pinion rotates, it's going to move the rack forwards, backwards, back and forth, and vice versa.
And then also one other note I would like to make. For a rack and pinion setup, the cylindrical gear is called a pinion. However, if you have two spur gears meshing with each other, usually the smaller gear is also called a pinion. That might get a little confusing, but hopefully it shouldn't be too bad. I don't know. It's been a while since I've learned about gears. But so creation of a gearbox, how do we do this? Well, first we have to figure out what like requirements we need. We need to figure out like, okay, so if I have this motor and I want to be going at this speed, I need to be using like this gearing with like two motors. And I need to have like, or like, oh, if I want to have two speeds, I want like a low speed and a high speed. The low speed has to use like this gear. It goes off of this gear to this gear. The high speed, like, oh, no, actually want this one instead. It's fun stuff like that. But anyway, once you have the gears that you need, in our case, we will be using a 52 tooth gear to drive the axle and 11 tooth pinion gears for the Neos. So once you have the gears you need and like a couple other stuff like, oh, I need to make sure or I don't design the motors to be like inside of each other. Once you have that, you can figure out the measurements you need, and you can start to create a plate to mount the components on, which will be the next portion of the lesson. This will take a while. I highly recommend everyone gets into Onshape and starts to create a new document so they can follow along with what I'll be doing. So I'm going to get rid of this part for now because I don't need it. Get rid of that. Okay. So we're going to start by creating the base plate. I have a reference I made last night. I'm going to pull up real quick. Okay, so let's see. Let's start by going to the front plane. Let's create a sketch here. So we want to have our output shaft. Let's put it out there for now. This is going to be a bearing that is 1 1/8 inches in diameter. So I'll just put 9/8 here. And then next we are going to have, or yeah, so next let's put the gear that, the 52 tooth, I think I said, gear that we are going to have on here. This is a pretty large gear, but the like diameter sort of the gear is about 2.6 inches. Just put that out there. And then since we also need to have our gears for the motors, so I want to have the motors about like there or so. I'll probably have the like a line branching off, so I know like, oh, this is about where I want this to be. And the 11 tooth pinion on the motor, that's going to be how large is this? 0.8 inches, I think? 0.6 inches. Okay. Always good to double check your references. So that's going to be 0.6 inches. So now, if this gear is 0.6 inches and this gear is 2.6 inches, what's the best way to make sure that they touch each other? It's probably not to actually mess with this line here, because like, oh, what if I want to change this to some other size later on because I made a mistake? I don't know. It's actually probably to set these two circles tangent to each other so they always touch, which is a pretty helpful trait in this case. So then next, okay, well, I have my sim like roughly, or not sim, sorry. If I keep saying sim, that's just because I'm a little more familiar with them. Use them a lot somewhere else. So if I say sim, it means Neo. I don't mean sim. Okay, so however, the Neo, there's part that extends like off the face of the motor. If I pull up a picture of a Neo, here we go. Yeah, okay. So in Neo, there's like a small little like part that extends out of the face by the axle. Um, th- this part will interfere with my plate if I try to just stick it in there. It just doesn't fit. And I need to have a hole so I can properly screw down the motor. So I will create a 0.8 inch hole for that because I'm pretty sure that's about the size it is. I think so. Yeah, that's what I have in my reference at least, so it better be. All right, so there's that. So that's that hole done. Now I need to create the mounting points for the sim. I guess let's do that next. I'll just draw a line across here. It sounds good to me. However, the mounting points, they are centered on the sims, or they're not centered. They're all an equal distance from the center of the sim. So if I'm trying to model two opposite points, the best way to do that is take the point at the center of this circle and go to this line, create a midpoint. Um, this ensures that this point and this point are always going to be the same distance from the center, no matter what position they're in. And then to make things easy, so I don't have something weird like that, I don't have to like mess with the measurement too much. I'll take both of these lines and I'll make them perpendicular to each other. Now, all they could do is change length, and that's about it. And it's starting to move a bit because just do be like that. Hold on a second. All right. Oh wait, that's the problem I'm having. I forgot to set the sim. How large are they? 2.36 inches. Yeah. Okay. So also, by the way, since I'm going to want to have an accurate model of how large my neos are for later, I am going to not do that. I'm going to use the dimension tool to set that to 2.36 inches, I think I said. Yeah. So now that's the size I need that to be. Then this, I'm a little tired. Yeah, tired. Sorry about all this. So then now that I have more or less the Sims dimensions, to finish off the mounting point, I need to have these 2 points be 2 inches apart, because that's how far they are on an actual Neo. So now that I have that, it's basically done. The only reason it's not defined currently, I think, is just because this can like, I don't want to, is because like, yeah, it still moves around. So what angle do I want to have these at? Well, I'm trying to keep it relatively compact. So I think a pretty good dimension to have would be, so if this is the diameter of the motor and I'm planning to mirror this whole thing across to over here, I probably want the, I probably want some separation between the two motors, right? In this case, I'll go with a total of an 1/8 inch of separation. But since I want to mirror it, it'll be a little annoying to just do that now. So I'll just dimension it from the center line here. And instead of going in with an 1/8 inch, I'll go with half the distance because I'm only dimensioning to half as far. So I'll go with 1/16 for now. So now this is fully dimensioned. So I have the very basic of, or the very basics of what I want to do so far put in. I have a central axle here, with a bearing and a gear that is this large. Then over here, I have a motor with a without a bearing, with a hole for the motor, and it has a gear that's this small. And then since I'll need to mount the motor, I have these points out here that I can use for that purpose. So now, this is great and all, but how do we actually make a plate for this? Well, I'm glad you asked. Not that I can actually hear anyone. I'll start by, well, let's actually, where do I want to start? I guess let's start by creating an outline of sorts around here. So I want to have a line that goes across from up here. I want this to be horizontal. There's no reason for it not to be. And I'll attach that at one side to the to the z-axis, and at one point to the top of this circle here. And then I also, over here, since I want to have a bolt somewhere up here, I don't know exactly where. I'll get to that later. But so, okay, somewhere up here, there's going to be a bolt. I'll start by just dragging a line out there, and then dragging another line out here. Make sure they're vertical so I can just set them tangent. And then I'll just put those there. So this is great and all, but I'm going to have a point somewhere in here. I don't know exactly where it is. I'll start by just drawing a line down here to make sure that one is vertical and that one is horizontal. And I'm going to do this to make sure that the hole I make, or in this case, since I'll be using the hole wizard to actually make the hole, because I don't know exactly how large it needs to be. But since I need there to be a hole here, and I want it to be like an equal distance from like this line and the outside of this circle, I will just draw like 3 lines, one to each object, and I'll make sure this one is normal to it, which means it sticks straight out. These one are, yeah, and then this is great and all. This whole, let me choose a point somewhere in here, but I want all 3 of these to be equal. So I'll select all 3 and I'll press the E key to make sure they're all equal. And now it's perfectly defined at one point that is an equal distance from all of these features. This will be very helpful for when I try to create a point or a hole, because I can just select that point when I'm ready for the whole wizard. However, now, like, this is a kind of sharp corner. I don't think I like sharp corners. I'll start with a center point arc, and I'll just round this off. I'll start at this hole here, because that's where I want the center of the radius to be. I'll go up to here, and I'll just pull it down to this side, so it's tangent there. That creates this nice, smooth, rounded edge there, which I highly suggest if you're making like a large plate like this, you make sure every corner is rounded. It will help so much. It makes it so much easier to deal with. You're less likely to hurt yourself when you're working with it. It just looks nicer. And then since I don't need these lines, I can just trim them away with the trim tool up here. Okay, so now I need to have a hole somewhere down here. I don't know exactly where this is going to have to be quite yet. However, I could find this actually. Well, let me do some quick calculations I forgot to do earlier, real quick. All right, so yeah, right around here. Yeah, let's go with around there. I want to have another hole at the bottom that I use for a standoff, because the way I'm going to have this set up In fact, I'll bring over the assembly I was working on last night. So I have a hole at the bottom that I use for this standoff, one for this standoff, and one for that standoff. I need to make sure that like these standoffs are not going to be hit by this gear when it's in motion. As it is, this is actually really close. I made a bit of a mistake while I was making this, and yeah, that's definitely too close. I'll have to change that a bit. But yeah, so I just need like various points around here, so this is going to properly hold itself together under the force that it is, or under any force it's under, or um, its own forces even. So yeah, basically, I, I, I need a hole down here, and I am going to have a like certain perimeter around the hole that I can use to like, oh, this is how large it needs to be. So I actually have enough material around the hole to make sure it doesn't like break out or something. Uh, this one up here is going to be a kind of bad example of that because I can't really get what I want with the spacing. That's just a flaw in the d- design I made. This is definitely not perfect by any means. There are many ways to improve on this, but we're going to go down here. We're going to create a hole. Let's go with 0.55 inches. That's a pretty nice number. And then we need this to be far enough away from here. I don't know exactly how far I want it to be, but let's go with, I think the hole or the spacer in, let's put it 0.25. Will that be good? I'm not sure actually. Um, let's just change this to 0.6 to make sure it's a bit over, and then change this to 0.3. Or not 0.3, 0.275. That'll be fun to remember. Also, this is one of the downsides of making like weird numbers like this. If it's going to be something that you're going to use somewhere else, I highly suggest drawing a construction line, and I'm actually going to do that right now, so that later, if you have to use that same number, and it has to be like the same from there to there, you could just very quickly just copy that line instead of like changing every single reference to that number every time you need to, you know, it gets complicated after a while. So we have this up here, then we need to have another one over here. Let's put this like here, say? That sounds good. So I don't need to make this like a certain size again. I can just, I'll make those circles equal to each other. That helps a lot. I don't need to worry about like, oh, this is however, yeah. Then I am going to have this, or no, not distance. I am going to create a construction line because like I just said, I want this circle to be a certain distance from this other larger circle. I'll just do that. That's tangent to the other circle. That's okay. I'll do that, and then just to make things a bit easier for me, I'll make these circles tangent. You may notice, hey, that's not defined, and actually, I think I forgot to, yeah. there we go. But hey, this isn't defined. You can still like move it a bit, even though you're not supposed to be able to. That's because like over here, since I was creating the line vertically, it's like Onshape just kind of automatically assumes, oh yeah, this is vertical, and that works for me because since I want this line to point directly at the center of this circle, because you know this is the distance from the circle. So because of like all the convenient assumptions Onshape makes, I don't have to do any other constraints. However, like up here, where this is at like a strange angle that doesn't fully make sense, this one, yeah, this is a really weird angle. So I need to make sure that since I want this circle to be a certain distance from this curve, it has to be normal to the curve so that it goes straight out from that curve. And as you can see, that fully constrains that circle. So now over here, this is for the motor. We're gonna do sort of the same thing, I guess. We'll just create two circles there, set these all equal to each other. And since I'm creating them like on certain points, I don't really need to actually go, oh yeah, this is going to be however large it's going to be. So that's actually a lot of the work done already, I think. Which is kind of scary considering how long it took me to plan this out. But now we have to, oh no, there's actually a couple other things I have to do. So the bearing, it's not just like floating in space, right? We have to actually like create something to hold the bearing. This is the central hole for the bearing. However, I want to have another circle going out from there. And let's make this circle 1/4 inch larger than the bearing. And then since we need more or less the same for the motor, make another circle here. This will go out. Dimension 1/4 inch. Non-shape died on me on my other monitor. So, okay, this is cool. We got that. Due to just the way the geometry works over here, we aren't going to need to create a circle for this over here. However, because it's pretty good practice, I'll just do that anyway. Go over here, create a circle the same size. You may notice that, yeah, this goes against what I was saying earlier. These circles are far from perfect. Yeah, or just this design in general has some flaws. Feel free to fix these if you can figure out how, but if possible, wait until after the like classes are over, because we are going to try to want to make sure everyone's doing it more or less the same way. And if someone, I don't know, I'm not a teacher. I don't know what I'm saying. So anyway, we're currently trying to create like a frame for the gearbox. We have all the circles we're going to need. We just need to actually like connect them together. Let's start with the external frame. We want to have a 1/4 inch like border kind of that goes around the entire thing. And like here we're going to want to be curved. We'll probably want it to actually we'll probably ignore that circle because it's not completely necessary to go out to there, and then there. And then we'll go down to there. I hope that makes sense. Oh yeah, so also, I know what I'm doing is kind of confusing, and then since I'm awful at explaining complex stuff like this, what I'm saying is probably fairly confusing as well. If I say something and you don't understand why I'm doing it, what I'm doing, something like that, please say something in chat. I know what I'm doing, but I don't know if you know what I'm doing. So yeah, if you're confused, don't be afraid to ask questions. Questions are very important. Someone else might have that same question, and you could end up helping both of you out. So please ask questions. Please, I'm begging you. All right, so anyway, back to the border work. We are going to set this to be, oh, wrong window. We are going to set this to be 1/4 inch out from there. That sounds good. And then since I also, yeah, let's go over here. So that's fine since we already have that like established kind of. However, over here, we want to have the line going out of there. How do we do that? Well, we have to actually create the line. Let's start here. This is fairly easy. How do you know, or spacing you want it to be at pretty much all of it? This is a very good question. So yeah, there's a lot of different measurements here. Some can be kind of confusing. Like here for the gears, there is a way to find that out from like the number of teeth on the gear and the like tooth pitch, which is like how far apart the teeth are. So you can find out the diameter of the gear from that and find out, oh, this needs to be this far apart. However, since I am currently trying to make like a frame out here, and I'm just like, oh, I want this to be 1/4 inch. I don't have like a exact like, oh yeah, this is exactly how you should be doing it type thing. However, right now, what I'm going off of is, okay, so the bearing I'll be using for here is a 1/4 inch thick. So I'll probably want to use a 1/4 inch thick extrusion. So like when I extrude this sketch out, I'll only extrude it out a 1/4 inch. That means that I probably want like these to be at the very least a 1/4 inch. So I'll just define that as a 1/4 inch for now because it's relatively simple. But then probably the most confusing spacing I have is these circles. That like these numbers probably look pretty random. That's because I'm cheating a little bit. On the like sketch I made last night that I'm using as a reference, instead of using the whole tool, I just used a diameter of 0.196 for each like bolt. And I'm just like, okay, well, I'm pretty sure that's what a number 10 bolt is, so I'll just go with that. And then from there, I did I think it was 3/16 of an inch around each bolt. And I said, okay, that's good. Which, again, like up here and parts of there, it's not perfect. And yeah, so that added up to a circle, like this circle, that had a diameter of 0.571. Since I'm trying to be a little safer here, I decided I'd just round that up to 0.6. And then the spacing here, since I had some issues with how I was doing it on, or in the model. How much spacing did I put around? Yeah, so there was a 1/4 inch between them the whole. Actually, wait a second. Am I doing this right? I'm not doing this right. Yeah, see, here's another good part of asking questions. It helps me realize when I'm probably doing something wrong. Okay, so let's see. So since I'm gonna create another circle around this one, so this here is the gear. Not all gears are perfect. They're not, well, no, most gears try to be pretty close to perfect. However, if I'm trying to put something near a gear, the like diameter I used here, it's not necessarily actually what I want. Like, because if I go back to the assembly I have, and I'm gonna hide this. So so if I'm trying to like create like, oh, I want these 2 gears to be touching, you see like, oh, like these gears, they don't actually touch perfectly. Like there's still some space in between each gear to allow for some freedom of movement. And that's because, well, the like diameter of the gear that I was talking about earlier, that only comes to about like there or so. Um, I really hope you guys can see my mouse. Um, I don't actually know if you can. I'm pretty sure you can. But basically, the like diameter of the gear that I've been using only comes to about halfway between like the like lowest point of the teeth of like one and the other, I guess would be a good way to try and describe it. I'm I'm not a gear expert, but I do know that like if you put something and it touches that line, it'll be inside the gear because the teeth like extend further out. Um, so the way I tried to do it was I had these holes here a 1/4 inch off from that line, and that put it a little close. So I'll actually, let's see, what's a good way to do that? So this is wrong, um, but I could probably build off that. So since I want to make sure this is safe, I'll create a larger construction circle here. Let's dimension this. I could probably still use a 1/4 inch there. However, that's going to probably be inside the gear. Wait, did I use a 1/4 inch? I swear I used a 1/4 inch. I did use a 1/4 inch. I'm not going completely crazy. Wait, no, that's, yes, I did use a 1/4 inch. Okay. So, wait, where is, yeah, okay, there we go. So since, like, that's not fully right, I need this to be a little farther out. Let's get rid of this, get rid of that. Get out of the dimension tool first. We can delete those lines because we don't need them. And then I want this, let's put it a bit further out to be safe. So construction line up to there. And then since so the spacer, it's going to be like a certain diameter. I don't know exactly how large yet. I'll probably just go with a 1/10 of an inch thick walls, which is not standard. However, it means that the spacers aren't going to go beyond that. Or actually, I could probably just use that line as the thing for the space. That would work too. I should do that. Learn something new every time I try to do this. However, that would require you to either cut down space or like trim down spacers with like a lathe or something, which is not easy, I don't think. I've never tried it, but I can't imagine it's easy. Or just get custom ones, which are probably expensive. So again, this design isn't perfect. There are plenty of places to improve. But so back to what I was saying, I need these to be like a certain distance from the safe distance here. Let's go with since I think a number 10 bolt is roughly 0.2 inches in diameter, and I want roughly 0.1 inch walls, and that means 0.2 plus 0.1 plus 0.1 is about 0.4. Actually, no, I don't need to do that. I just need 0.1 plus 0.1. So yes, let's just set that to 0.2 then, right? Because that'll be roughly the diameter of the bolt, and plus the 0.1 inch diameter walls. So let's just go with that for now. I think that's about good. This will probably be safe from the, it should. I can change it later if I need to. I'm pretty sure. Yeah, that should be fine. So then, since I have this done here, I need to redo it up here. Oh yeah, also, by the way, if any of that really crappy explanation I didn't make any sense, please let me know. Because I don't know how much sense that made. I mean, I hope it was easy enough to understand, but I'm going to drink some water because my throat's starting to die. All right, so I want to have. Okay, so yeah, we were working on the border. Right now, we are trying to get a line between these two circles. So I want to have this line be tangent to these, so I don't just have like some random like bulge in my plate. This is fairly simple. You just tangent here, tangent there. Okay, that's good. And then since we told ourselves that if it's even going to be an issue, which I'm not sure if it will, we're just going to ignore that circle there. Let's just create a line from this circle to this circle, which doesn't look like it's going to be an issue, which is good. So let's set that tangent to there, and let's set that tangent to there. Now, you may notice, like, okay, this is fine. This is all a solid line. However, over here, this is a construction line. That's not good. That's not right. We can go back over here to the center point arc, which is my favorite arc, by the way, if you can't tell. And we can like click at the center of this circle here, can go out, oh, I want it to be there, and then just drag that down to that point there. And now we have a solid line that goes around. If I mirror this whole thing across the z-axis, this will be a solid shape. It just doesn't say it is right now because, like, yeah, that's open currently. However, I assure you it will work properly. I'll just be doing that at the very end because I don't want to have to, like, keep finding small details I've changed and mirror it. So, like, this is an example of when, like, oh, it's good to have a pretty good idea of what you're doing in advance. Like, oh, I want to have this. Um, yeah, it just helps a lot. So now we are going to keep making the interior border. So, okay, we have this here, and then it curves, and then it intersects with this. So I'm going to draw a line down. I think that's about right. But just in case, since I don't know if I want this to be exactly horizontal at that point, I can just put it a bit before. Looks good. And then since I want this part to be curved, um, I'll go back up to the center point arc. Let's put it there. Let's go about there. Line. That looks like that's about right, I think. So now I want these two lines here to be parallel because this is part of the border there. So I'll go up here, hit parallel. And then I want these to be tangent if they're not already. So I'll set those tangent. Same for that one up there. So now that's like a nice clean curve. However, it's not like I don't know how far I want that to be. I'll just go back up there. That's a 1/4 inch. This could be a 1/4 inch. That's defined. So that's pretty good there, I think. Yeah. Now, I'm not going to put a line there yet, and you'll see why in a little bit. But down here, I need to finish off the inside border of this. So I'll just, oh, it looks like if I do it like that, it will automatically make the line parallel to the outside border. That's what I want, so I'll accept that. And I'll dimension this. That's not what I want to dimension. I'll dimension that. I want that. There we go. I have the tool. Okay, so set that to a 1/4 inch. And that's just about exactly where I want that to be. So now, I have the outside border done. Now I need to actually connect these circles on the inside. I'll start with connecting this here to the outside. We're gonna start down here. So since I want to have a like bar kind of that goes up from this circle down here up to this circle, I only have to draw this side of the line because it gets mirrored across. And then I want this to be, since I'm going to make like these like struts, I guess. I don't know what's a good term for them, but basically, since I want these like connectors to be a 1/4 inch wide, which is the same as this bar over here is thick. Since I'm mirroring it and I'm only drawing half it, I only have to make this like or I only have to make this half as far from the like center line as it is actually going to be. So in this case, since I was doing 1/4, I'll do 1/8 instead, because 1/8 plus 1/8 equals 1/4. All right, that's good. I also want to have one going from there to there. This one's a little more complicated. And actually, there's something I want to do here. So I have these lines that go out to each circle. I'm probably going to do that for just every point. So yeah, that one goes out to there. I'll have another one that goes down to there. And why not? I'll put another one that goes up to the very top up here. Which reminds me, I need to finish off the outside border here. I'll drag that line out. And then since I also want to have a connector that goes from the top up here to that circle there, I'll go straight down to that there. And that's a solid thing now, so it'll do that. So I want this to be 1/4 inch, because that's the measurement we've been using so far. And then same as down there, I want this to be 1/8 of an inch apart. So 1/8, there we go. Okay, that's defined. And then now I want to, okay, so this part's a little more confusing. There are good ways to do it, and then there's my way. I'm actually gonna start with the good way. That's probably a good idea. So I want this to like extend out a fair way. So I'm going to use the offset tool. I think we covered this in lesson 2. I think, yeah. And this is going to extend out, like same thing over here, since I'll have to do 2 of these, one in each direction. This will extend out 1/8 of an inch, so set that 1/8. Then now let's do the same thing, but the other direction. So that is 1/8 too. And then actually, I think you can, yeah. So if I only want this to go like a certain, like, or if I want this to connect to a certain point, I can just, oh, okay, I want that to connect there, I want that to connect there. And this uses the like default on-shape thing. If you drag a line or if you drag a point onto a line, it assumes that you want that point to be attached to that line. So that's pretty good there. We have a like 1/4 inch wide bar going from there to there. Now, we could do some. Oh, actually, I need to do the sim up here. Hold on. All right, so that goes there. And then we're going to use the offset tool again. The key for that is O, by the way, in case I forgot to tell you that, which I very well might have. So we are going to create another line, same as before. It will be 1/8 apart. And then same as before, we're going to create a second line, the opposite direction, that is also 1/8 away. And that's not what I want. And now I have these lines I can do, I can grab the point. Same thing I did before where I just, there's so many constraints, where I just drag it onto that line and it attaches. Do that over here too. All right, so if I were to extrude this now, after that was mirrored, of course, I would have a like frame goes around there. There's a bar going to there. These aren't attached to each other. I'll show you why in a little bit. And I mean, yeah, it looks pretty good so far. There's no issues I see. Um, I say it's time that I actually show why I did not connect this and have not connected these yet. And that's because I like rounded corners. Remember how I was talking about up there, and I like rounded that corner and trimmed off these lines. Actually, speaking of trimming, I can get rid of the outside of that circle because I don't want that. I don't care about that. So, um, a pretty easy way to create a like nice like rounded corner, or well, actually no, first I'm going to discuss why rounded corners are so good. First of all, yeah, they look super nice and stuff, but also if you're trying to create a complex plate like this, chances are you're going to be using a CNC or a mill, and a limitation of a CNC or a mill is that if you're trying to like cut a corner, the like all corners they make are rounded because they have um, what are basically these drill bits that are designed to cut side to side in addition to like up and down. Um, and the bit can only be so small, and it's always like rounded to at least some point. So basically, like a sharp corner like that, you can't actually make a part like that unless you're doing like 3D printing or something. But it, if you can afford a metal 3D printer, you can probably also get significantly better training than this class. So anyway, I am going to show you how to make a nice rounded corner. Um, so we're going to start with a circle. We're just going to drag it out to this line. You'll see that when you drag it out to the line will be highlighted and the tangent icon will show up. This is good. We want that. We are going to click on that line. Then we are going to open up the tangent tool again. We are going to go over to this line here, set that tangent. All right, so now we have a curve. Thing is, how large do we want this curve to be? We actually have a lot of room here. We can make it more or less whatever size we want. Personally, I like to go with 0.1 inches, I think. Yeah, sounds nice. So, or actually, a radius of 0.1, so the diameter would be 0.2. There we go. That looks nice. So it's this like nice rounded curve. I don't need to like, or, and yeah, this is like pretty much just like whatever size you want. I'm guessing that it, since you're on a team, your mentors, if they want to do this kind of thing, they'll probably have a like radius or diameter they want you to use, um, or possibly just one that gets used on the robot a bunch, and it's like, oh, I should probably use this one so it's actually consistent with everything else and all that. But basically, yeah, there will probably be like some radius you'll be using more or less everywhere. But the problem here is, okay, it's a circle, but there's all this curve. I don't need that. that's where the trim tool comes in. Again, you can just trim off that side and look, you have a nice rounded curve. It looks super nice. It's very pretty. So now, see how large that curve is? See how small this gap is? Here's the reason why I said we didn't need to have a like line like here or there that connects that to that or there. If I put a curve in, look, there's like so much space, and this is smaller than that one. So I'm just going to, okay, I want that to be tangent to that circle, so use touch. And then since that's still resizable, I'll just set these equal to each other. And then once Onshape finishes loading, all right, so I have that, I can just trim it. It's done. So, starting to run out of time. So yeah, now I'll just put curves everywhere because curves are nice, you know. So you just go around the model, these equal, let's trim that off. Continuing on there. Those tangents, set those equal, trim that. That tangent equal, it's not what I meant to do. There we go. And then get rid of that. This is like a bunch of the same work over and over. I recommend you just try to get as many corners as you can, not necessarily like, oh, you have to get every single one, because remember, you can just finish this as your practice activity. You don't have like anything else you have to work on. So I'll do that, that tangent. So yeah. But basically, you just keep going around doing that. I'll yeah, there, that, trim that, and that, since that line was in the way.
One thing to note is that all of these curved sections that we're making are going to eventually become holes in the final extrusion of the plate. And we do that in order to help save on weight and material. So a lot of sections, they just get cut out just so that it weighs less and the entire gearbox will be less of a burden on whatever it's attached to.
So I'm not actually going to get every single corner here just for the sake of time, because like there's these corners. I don't need to do those yet. I'm just going to get as far as I can to show like what this is supposed to look like when it's done, more or less. So set that. Set these equal, and let's trim out that and that. So that tangent. I gotta trim all that off now. There's a lot of stuff down here I gotta trim. Get rid of that. All right, so I think that's about it. Yeah. So now, so that's about as far as I need to like really do. Although, if I was going to actually make this a plate, and in fact, for your practice activity, you are going to have to put curves in each of these corners so it works properly. Actually, I am going to put a curve here. This corner is going to be a bit special. I don't think if you, yeah. The like math and geometry, it just doesn't line up quite right. So for here, instead of setting like this equal to that, we are going to just make this tangent to all the sides. That was important. Make sure you have that one. But I could barely keep up. Yeah, that's just because I'm trying to go as fast as possible right now. It's also because I was doing this for like an hour straight last night, so I got tons of practice quickly doing this. Don't worry about you. That's not on you. That's just me not managing time properly. Yeah. So we're gonna try to mirror this across the z-axis. So first, let's just make sure we have everything selected that we need to be selected, which it looks like we do. Oh, no, we don't. We don't have this selected. Let's add that. No, it's not control. It's just normal click. And then let's add this. Okay, that all looks right. Anything else? No, I think that's about it. So we're going to mirror this across the axis. Oh, we forgot to mirror that. Okay, there we go. So that's our plate. And then since I'm still rushing a bit, we're going to extrude this. And wow, that's not at all what I want. So I need to go select every sketch region because I was lazy and didn't trim anything. Or, well, I trimmed some stuff, but not enough. I'll have to, and then you might have to like make sure like go in, select all these. Oh, looks about right. And then we only want this to be 1/4 of an inch thick. So we're gonna set that at 1/4, make sure I have everything. That's everything I put on there, yeah. So it's not quite done yet, but yeah, you can definitely see this plate has come really far in such a short time. Like, this looks like something that would actually go on the robot. Of course, you would probably make like certain stuff like that a little thicker than I did. But yeah, so now we're a little pressed for time, so we're gonna hold off on the plate here. We'll probably pick up on that next class. And we are going to go to the 10-minute quiz, or probably not actually 10-minute quiz, but you get the idea. All right, so everyone, if you're still awake, I really hope you're still awake. What purpose does a spur gear serve in a gearbox? Or actually, not spur gear. Hold on, I put the wrong thing in there. Okay, what purpose does a pinion gear serve in a gearbox? Does anyone remember? I mentioned it briefly at the start of the presentation. Distribution of power? Yep, let's see if anyone else can changes the plane. Not quite, that's a beveled gear, I think you're thinking of. Converts rotational motion into linear motion. Okay. All right, so this is partially because we didn't properly explain this at the start, I suppose. So basically, in a gearbox, not in a rack and pinion, they are slightly different. However, in a gearbox, the pinion gear is the part there. This is the smaller gear. In this case, it is driving the larger gear, which, as some extra trivia, is called a bowl gear, although I've never heard that before. I just searched it up earlier today. And yeah, so in our gearboxes, it takes the like spinning in from the motor and it transmits that to this gear, to this shaft. So let's go back to where we were. What purpose does a motor serve in a gearbox? All right, these answers look pretty good so far. We have powers the gears, runs the gears, turns the gears, torque and power. And yeah, that's pretty much what it is. I mean, yeah, I'm not really sure I can actually do much of a better explanation of that myself. So let's turn the questions over to Dexter now. He's going to do the last two.
Okay, so what does an encoder measure when it's installed in a gearbox? Yep, these basically all right answers. So the encoder, depending on where it's placed, it's just going to count the amount of rotations that the motor itself or a gear is doing per minute, and then it can send that information to a motor controller to help control the motors, control how fast they're spinning, and so on. So yeah, those are all correct answers. And then finally, what do the plates of a gearbox do? What is the purpose of that thing we just spent most of today's lesson working on? Yep, so stability helps keep everything stable. It also helps mount all of the internal parts. And yep, it also helps protect the gears, for the gears mounting, all that. It basically functions as the housing for everything inside the gearbox, makes it all work. So, yep, those are all good answers. And it seems that right here has learned hopefully a good bit about gearboxes, what they do and how they function. And so the next lesson, we'll be finishing up the gearbox, which is going to be much easier. The facing was the hard work. Now we just have to use MKCAD to import the proper pieces and assemble them all together. But so I guess just remember for your practice, just make sure that you have the faceplate fully created. You can, of course, reference this Zoom meeting after it's been uploaded to the resources page. And Pierce, anything else to add?
I just want to add that in case everyone has forgotten the link to the resources page, that would be right here. I highly suggest that you save this link, but just in case, I'm just kind of dropping it in chat there again. And that's where we keep the practice. activities, all kinds of stuff like that. You guys already know all this. But yeah, that's about it. Thanks for showing up. Yep, we are glad to help. If you have any questions, feel free to ask them. Otherwise, you are free to go. Your extrusion won't register the struts. It is only doing the whole gear. That's the wrong thing. So it sounds like you're talking about, let's go back to extrude. So like what parts is it only doing the whole gear? Do you mean like this like big circle in here? Yeah, okay. Uh, have you, okay, so first of all, is it a construction circle? Because it should be. Yeah, okay. Uh, wait. Thinking. So when you went to extrude it, did you like deselect the faces or if you could screen share, that would probably be helpful. I'm not sure if you can. Highlighted the whole thing. Uh, uh, all right. I think I might have fixed it. Try now. Uh, can you screen share or? Oh, okay. So it's weird. Um, have you tried to make sure that? Oh, I think I see the problem. So if you go back to the drawing, um, you see the like smaller gear part, like the gear that would go around the motors. Um, Part of that needs to be like a solid line. So if you go into sketch one, yeah, okay, so um, uh, try setting, so yeah, so one of those circles has to be like a solid circle, and then, yeah, the circle that the lines go to has to be a solid circle. Because if it's like not like a closed shape, um, on shape can't like extrude it out properly. Yeah, so if you set that one to solid, all right, so that will probably solve it. Let's see. And then, yeah, go to extrude one. And then just make sure everything you want is selected. Huh? Oh, it looks like one of those lines is a construction line. But I think you see like more or less how it's supposed to be done, right? I think. So is
Yeah,
that
I get it.
yeah? All right, sweet. We are glad to be of assistance. Thanks for showing up. That'll probably be about it then.
Okie dokie. Thank you. Have a good day.